Our Troubleshooting Electrical Problems, Mike Bush, Savvy Aircraft Maintenance Management Incorporated. Mike is joining us again. He's been a very popular presenter, and we're glad to have him along. A CFI, an A&P with an IA. He was also Aviation Maintenance Technician of the Year in 2008, and of course, an EIA member. And Mike, with that, I'm going to turn the audience over to you.
Okay, let's get my mic unmuted. You hear me now?
Sounds good.
Presumably you do. Okay, now let me try to get my screen up. Can you see that?
There we go. We've got you.
Okay, excellent, excellent. So hopefully the technical issues are over. Welcome everybody. This is the 14th in a series of maintenance-oriented webinars that normally are done on the first Wednesday of every month. You may notice that this is not the first Wednesday of the month. We moved this particular webinar a week early because next Wednesday, which is when the webinar normally would have been scheduled, I'm going to be in Florida speaking to the Flying Physicians Association annual meeting. And the next one of these, which would normally be the first Wednesday of August, August 3rd, is going to be pushed off a week till August 10th because of AirVenture. So this one is a week early. The next one will be a week late, and then hopefully we will resume our normal schedule of the first Wednesday of every month. Tonight's webinar is also the third and last in a series of 3 webinars that I'm doing on the subject of troubleshooting. The one that we did in May was on the general principles of troubleshooting. The one we did the 1st of June was on diagnosing common engine problems. And tonight we finish up the trio of webinars talking about diagnosing common electrical problems. And of course, I'm Mike Bush. I'm an A&P IA. I'm a pilot for 46 years, 7,500 hours, aircraft owner for about 43 years. I write the monthly maintenance column for Sport Aviation called Savvy Aviator. And I'm the president of a company called Savvy Aircraft Maintenance Management, Inc. that is in the business of managing maintenance of owner-flown GA aircraft. Tonight's webinar will be a little bit shorter than usual, which will give us some extra time for questions. When we get to the Q&A session at the end, I will have my email address up. And so anybody who asks a question and does not get an answer during the webinar tonight, or if you have a question that's a little off topic or one that you think is specialized and might not be of general interest to the participants, please feel free to email me your questions, and I will attempt to answer every one that we don't answer during the live session tonight. We'll be talking about some common electrical glitches. Obviously, in a webinar like this, I can't get very type specific, so this is going to be sort of on a generic level, but we'll be talking about diagnosing charging system failures, premature battery failures, short battery life, problems with short alternator life, noise in the radios, weak starting, and then just a couple of wrap-up comments about troubleshooting electrical problems in general. So let's start with talking about charging system failures. This is a very simplified schematic diagram of a typical aircraft charging system. And as you can see, it's got a fairly small number of components, an alternator. I won't be talking about generator systems tonight, but they're relatively similar. A voltage regulator, that supplies field current to the alternator and varies that field current to maintain constant alternator output voltage. Some kind of overvoltage protection device, in this case an overvoltage relay, which takes the alternator field away in case something goes wrong with the regulator and causes the alternator output to rise to a level that might tend to fry avionics and so on. This is a protective device to make sure that a regulator failure won't take out a lot of expensive stuff. An alternator field switch for turning the alternator on or off. In some aircraft, it's a split master switch that's combined with the battery switch. In other aircraft, it's just a separate switch. A circuit breaker, a field circuit breaker, or in some cases a field fuse that provides protection for the field circuit. Usually, it's a fairly small amperage device because typically alternators under normal circumstances will draw no more than about 2 amps of field current, and that's typically when the engine's not running, and the higher the RPM, the lower the field current that they draw. So normally this is a small amperage device. And then a big, a high amperage breaker for the alternator output that protects the heavy alternator output wiring. So that's basically the componentry of a typical charging system. In more modern designs, the regulator and overvoltage relay tend to be combined into a single unit, which can be called an alternator control unit or a field control module, but basically all it is a regulator with overvoltage protection built in. Older aircraft tend to have a separate overvoltage device, and newer ones tend to have overvoltage protection built right into the regulator. So let's suppose that we have a charging system failure, and all of a sudden the alternator is no longer charging the battery. We see a discharge. If we have an alternator fail light, it comes on, or if we have a low voltage light, it comes on to tell us that something's wrong. So how do we go about troubleshooting this problem? I can tell you that in my experience, unfortunately, mechanics aren't very good, or most mechanics aren't terribly good about troubleshooting these things, and they tend to respond to problems like this by replacing things. And there have been an awful lot of alternators replaced and regulators replaced when it turned out that the problem really wasn't the alternator or the regulator at all, but was simply a bad connection or a broken wire or something like that, which is the problem a good deal of the time. So it's real important from an aircraft owner standpoint that you insist that when you have a problem like this, that the problem be troubleshot in a methodical manner, and don't allow expensive components to be replaced unless you're quite sure that those components have actually failed. So let's talk about how we would troubleshoot a charging system failure in a methodical manner. And it's really very straightforward, and normally should not take more than, I don't know, a half an hour or so if a mechanic knows how to use a test meter and read a schematic diagram. Typically, the first thing we're going to want to do when we troubleshoot a charging system problem is to make sure that the alternator has everything it needs in order to charge the battery. And basically, it only needs 2 things. It needs to have mechanical rotation of its drive shaft, and it needs to have field voltage from the regulator. So the first thing we want to do is make sure that the alternator is turning. Seems like a pretty elementary thing, but it's surprising how often that's the problem. Now, there are basically 2 kinds of alternators. There are belt-driven ones and gear-driven ones. On a belt-driven alternator, the alternator drive shaft has a pulley on it, and it's driven by a drive belt, and normally it's easy enough to just take the top cowling off, take a look at the alternator, rotate the prop, and make sure that that the alternator is turning and that it hasn't thrown a belt or something like that. If it's a gear-driven alternator, the drive is actually hidden, so we need to get a little more clever, and typically you can look into the cooling slots on the back side of the alternator, on the non-drive end of the alternator. Shine a flashlight in there and turn the prop and see if you can see the rotor moving. Actually, most alternators have a little fan inside, and if the alternator rotor is turning, you can see the little fan blades turn. But basically, the first step is to make sure that the alternator is actually turning. If it's a gear-driven alternator and we find that it's not turning, then we probably have to remove the alternator and check the drive hub and see if it's sheared or something like that. Assuming that the alternator is actually turning, the next step would be to put a voltmeter on the alternator field terminal and make sure that with the battery and alternator switches turned on, that the alternator is getting field voltage. And if we make this measurement in the hangar with the engine not running, hopefully, we should see something approximating battery voltage at the field terminal, either 12 or 24 volts, depending on what kind of system you have. If the alternator is turning, and if the alternator is getting field voltage, then it is getting everything that it needs, and therefore the alternator itself must be the culprit. But if the alternator is not getting field voltage, then we can hardly, then it's pretty clearly that it's not the alternator's fault, so we need to dig a little bit deeper. So the next thing we would do, again, the airplane is sitting in the hangar with the top cowling off and engine is not running, and we've got the battery and alternator switches turned on to energize the system. We'd move our meter probe to the field terminal of the regulator or alternator control unit or field control module, whatever it's called in your particular airplane, to see whether the regulator is furnishing field voltage. If the regulator is furnishing field voltage but the alternator is not seeing it, then we have a broken wire or a bad connector or something like that. If the regulator is not furnishing field voltage, then we need to dig a little bit deeper and see whether the regulator is receiving power. If the regulator is receiving power but not putting out field voltage on its field terminal, then the regulator has failed. If the regulator is not receiving power, then it's obviously not the regulator's fault. We have to keep backing up and see whether the overvoltage relay is furnishing power. This is assuming that the overvoltage relay is a separate device and not combined into the regulator. Is the overvoltage relay getting power? Is the alternator field switch furnishing power? Is the alternator field switch getting power? Is the breaker furnishing power? And so on. And so we just work back with our meter until we find where the power is being, the field voltage is being lost, and we have found our culprit. And as I said, more often than not, well, maybe not more often than not, but at least a lot of the time, the problem turns out not to be the alternator or the regulator, but simply a broken wire or a bad connector someplace. If the problem is intermittent, we frequently find problems with the alternator field switch itself. Sometimes the field breaker is bad. So when you have a charging system problem, don't automatically assume that it's the alternator or the regulator. You want to go through this troubleshooting process to find out exactly what the problem is, so you don't wind up replacing expensive parts that don't actually fix the problem. Once again, just to review this very quickly on a word slide, first step is to check to see if the alternator is actually turning. If it's not turning, then if it's belt-driven, there's a problem with the belt. If it's a gear-driven one, then perhaps the drive hub has sheared. If it's turning, then the next thing is to find out if the alternator is getting field voltage. If it's both turning and getting field voltage, then the alternator has everything it needs, and if it's not charging the battery, then the alternator itself is faulty. We can do some more tests about the alternator to find out exactly what's wrong with it. We can put an ohmmeter across the field and see if the brushes and slip rings are bad. We can do some tests to see if the diodes are bad, but it really doesn't matter, because if the alternator has anything bad about it, we're going to have to remove it and send it out to be repaired. So usually it doesn't make sense to troubleshoot alternator problems down to the component level, because whatever is wrong with the alternator is just going to have to come off and be repaired or exchanged. If the alternator is rotating and getting field voltage, then it's not the alternator's fault. So we have to go backwards and see if the regulator is putting out field voltage. If the regulator is putting it out, but the alternator is not getting it, we probably have a broken wire or a bad connector in the lead between the regulator and the alternator. If the regulator is not putting out field voltage, we want to see if it's getting voltage in. If it's getting voltage in but not putting voltage out, then the regulator has failed. If it's not getting voltage in, then we have to back up further and check the overvoltage relay field switch and circuit breaker. But it's a very logical progression, and it normally should not take very long to go through this process. And I would encourage you to make sure that when you have problems like this, you make sure that your mechanic has actually gone through this whole process before you agree to start replacing things like alternators and regulators, because frequently they're not really the culprit. Let's talk about another issue, which is short battery life. In my experience, aircraft battery, that's properly maintained and in a system that's properly adjusted, ought to last 3 to 5 years. I just replaced the battery in my airplane. It was 6 years old the last time. I checked the logs. The last time I replaced it, it was 5 years old. If you're getting notably short battery life, it's certainly anything less than 3 years, then there's probably something wrong. And what's most likely wrong is that the system bus voltage is not properly adjusted. Batteries, unlike almost everything else in our airplanes, batteries are exquisitely sensitive to bus voltage. A 12-volt battery needs about 14 volts, plus or minus a couple tenths, to charge properly. And a 24-volt battery needs about 28 volts, plus or minus a half or so, to charge properly. If the voltage is lower than it should be, then the battery will last a long time, but it won't accept a full charge. And that will be bad if you have a charging system failure and wind up operating on battery only, because if the battery hasn't accepted a full charge, then you will have less time to get the airplane on the ground than you should. So we don't want the bus voltage to be lower than spec. But even more importantly, we don't want it to be higher than spec. Because if the bus voltage is higher than it should be, even by a few tenths of a volt, the battery overcharges. It outgasses excessively, and the plates in the battery will deteriorate at an accelerated rate, and the battery will lose its ability to hold a charge much earlier than it should. So we want to check our voltage often and accurately. By accurately, we need a digital meter that can read to the nearest tenth of a volt. Nowadays, most of our airplanes have something either on the panel or on the yoke that is capable of measuring bus voltage to the nearest tenth of a volt. An engine analyzer, a JPI or something like that, typically has a digital voltage readout. A storm scope has a digital voltage readout. A Garmin 396 or 496 or 696 portable GPS has a voltage readout. It actually doesn't appear by default, but you can configure it to display it. You know, some aircraft just have a dedicated digital voltmeter on the panel. It's a real good idea to have something in the cockpit that lets you read bus voltage accurately to the nearest tenth of a volt, and to keep track of it and make sure that it's what it ought to be. The service manual for most aircraft has specific information on what the optimum bus voltage should be. You should look it up. Maybe you even put a little placard on the panel to remind yourself of what it is. And if the bus voltage gets off of the specified voltage by more than a couple of tenths of a volt, particularly if it's on the high side, it's worthwhile to have the regulator adjusted to get the voltage right on spec. Adjusting the regulator is normally a very simple procedure. It's just a screwdriver adjustment on most regulators. Even on my twin, where there are dual regulators and you have to parallel them, the whole procedure takes less than 30 minutes. And for single engine airplanes with a single regulator, it's usually a lot quicker than that. So check your voltage often and accurately, and if it gets more than a couple of tenths of a volt off of spec, get it adjusted. That's probably the most common reason that batteries wear out early, is because the bus voltage is too high. Both Gill and Concord, the two manufacturers of certified aircraft batteries, recommend doing an annual capacity check of the battery, which consists of charging the battery fully and then discharging it with a specified load, and seeing how long it takes to discharge. And by measuring the ampere-hour capacity of the battery that way and comparing it to what it's specified, what the specs, the ampere-hour spec for the battery is, we know when it's time to replace the battery. I think Gill recommends replacing it when the capacity deteriorates to 80% of spec, and Concord recommends 85% of spec. So doing an annual capacity check is a good idea, because it gives you an objective way of determining when to replace the battery and not risk getting stranded someplace. Short alternator life. We can sometimes run into airplanes that go through alternators quite frequently, and that gets kind of painful because alternators tend to be pretty expensive. If alternators aren't lasting a long time, and at least in my experience, alternators ought to go at least 1,000 hours and often to engine TBO. But if you're replacing them a lot more often than that, there are typically two culprits that are responsible for short alternator life. One is heat and the other is vibration. So let's talk about each of those for just a moment. Alternators require forced air cooling. Among other things, the alternator has a rectifier assembly in it that has 6 big high-power silicon diodes that rectify the alternating current that the alternator produces into direct current that the aircraft needs. And like any other high-power semiconductor device, these things need air cooling. And if they aren't kept cool, they will burn themselves out. Now, alternators are sometimes mounted up in the front of the engine. For example, like a Bonanza or my twin Cessnas, where the alternator is right up front in the 150-mile-an-hour air, and those typically get pretty effective cooling, and we don't often see those fail because of excessive heat. But alternators that are mounted on the back of the engine, either on the accessory case of the engine or belt-driven alternators that are mounted back behind the engine, like on most single-engine Cessnas, for instance, are mounted in an area where there's very little airflow and where the air tends to be pretty hot. And those alternators typically need to have a source of cold air blowing on them in order to get proper cooling. That's usually accomplished by something called a blast tube, which is just an air duct that is set up to take cold air from up on top of the engine and blow it on the non-drive end of the alternator where the cooling slots are. It's quite common for these blast tubes to either disappear or get mispositioned in the course of maintenance, especially during engine changes and so on. And if the blast tube is not present or is not positioned correctly to be blowing copious amounts of cold air on the back of the alternator will overheat, particularly the rectifier assembly in the alternator, and will not live very long. So if you're going through a lot of alternators, that's one of the things you want to check, particularly if your alternators are mounted in the rear part of the engine compartment as opposed to right up front in the air blast. The second big culprit is vibration. We see vibration-induced failures more often with belt-driven alternators than with gear-driven ones, because the belt-driven alternators typically are mounted on some sort of a shock mount, and if there's a problem with the mount, or the bolts aren't torqued properly, or the belt tension isn't correct, the alternators can vibrate pretty badly when the engine is running, and vibration like that will cause premature alternator failures. There are a lot of crimped connections inside the alternator where the various components of the rotor and stator windings are connected, and if those things are subject to a lot of vibration, they will fatigue fail and cause the alternator to fail. So that's the other thing to check in the case of an airplane that's going through a lot of alternators, is to make sure that the alternator is not subject to excessive vibration, and particularly in the case of belt-driven alternators, make sure that the alternator mount is secure and undamaged, and that the belt tension is correct. Another common electrical squawk, or maybe avionics squawk, however you want to classify it, is noise in the radios. And there are a couple of basic different kinds of noise. So the first thing that we want to do to troubleshoot noise in the radios is to figure out what kind of noise we're talking about. The two most common kinds of noise that we find in radios are alternator whine, which is a sinusoidal tone, if you will, that whose pitch varies with engine RPM. The way that we can confirm that this whine is coming from the alternator, first of all, is to note that its pitch varies with RPM, and second, to note that if we turn off the alternator field switch, the noise goes away, and when we turn the field switch back on, the noise comes back. The alternator whine is caused by excessive ripple on the aircraft bus. I'll show you a picture of that in just a moment. And it's virtually always caused by one or more rectifier diodes burning out in the alternator. And as we said, inadequate alternator cooling is frequently responsible for these diodes burning out prematurely. But if a diode fails in the alternator, the output of the alternator will have a large AC ripple component, which I'll show you in a moment, and we hear that in our headsets and so on as a whine, which varies with engine RPM and goes away when we turn off the alternator. The other common source of noise in the radios, and in fact I just had a problem with this on my own airplane that I had to fix a couple weeks ago, is ignition noise. Ignition noise sounds totally different than alternator whine. It is not a tone. It is, for lack of a better word, it sounds like static. If you've ever been listening in your car to an AM radio station, a weak AM radio station, and a big giant truck pulled up next to you, and you heard a bunch of noise in your radio, that's what ignition noise sounds like. Again, the way we diagnose that, first of all, is to note that it has that staticky quality, and second, that it disappears when one or the other mag is turned off. In my airplane, because it's a twin, there are 4 mags, and when I first started hearing this impulse noise in my radios, I cycled in flight. I cycled 1 mag off at a time until I discovered that when I turned the right engine's left mag off, the noise went away. And that confirmed to me that, first of all, it was ignition noise, and second of all, that it was associated with the left mag on the right engine, which is the big first step to troubleshooting this problem. If you have ignition noise in the radios, The most common cause for that is that the P lead, which is the wire that goes from your ignition switch in the cockpit to the terminal on the magneto and is used to ground out the mag when you want to turn it off, that P lead, which is a shielded wire, has had its shield ungrounded, and the most common reason for that is that where the shield is grounded to the mag inside the engine compartment, the shield has just fatigue failed because it's subject to lots of vibration, as is anything that's hung on an engine. And if the P lead shield ground gets disconnected, that P lead, which is no longer shielded, just becomes a big antenna that radiates ignition noise into all radios and so on. So that's the most common reason for ignition noise. It can be a bad magnetocapacitor. It can be a bad magneto noise filter if you have one. Most installations don't have a separate magneto noise filter. It can be a defective spark plug. Each of our spark plugs has a noise suppression resistor in it, and there's a history of those resistors, particularly in Champion brand spark plugs, going bad, and that can cause ignition noise as well. But the first step, of course, is to verify that it's ignition noise and to isolate it to a particular magneto. And then the first thing to look for is an ungrounded P lead, and if that's not the problem, then you need to look a little bit further. There are some other things in airplanes that can cause noise in the radios. Strobes can cause noise. Again, you diagnose that by noticing that the noise, that's also impulse noise, but it's very slow, and you hear it at the strobe repetition rate, and you know when you turn off the strobe it goes away, so you know it's strobe noise. And most often that's also a loss of grounding, because the wiring between the strobe power supply and the strobe light needs to be shielded, and the shield needs to be grounded, and so on. But another thing that can cause noise in the radios is anything with a motor, electric motor, particularly ventilation blowers and things like that. And again, the way you troubleshoot these things is to start turning things off, turning switches off, pulling breakers, whatever, until the noise goes away, and then you figured out what the source is, and then you can hone in on it. This is a quick simplified diagram of an aircraft, typical aircraft alternator, which basically just has three components. It's got a rotor, which is the thing that is mounted to the shaft and turns when the alternator drive shaft turns. The rotor is supplied with field current through some brushes and slip rings. There's a stator assembly, which are the big heavy wires on the outside of the alternator that don't turn, where the three-phase alternating current is induced by the rotation of the rotor. And then there's the rectifier assembly, which has 6 silicon diodes and takes the three-phase AC that the stator generates and turns it into fairly good DC, which is what the airplane needs. When we have alternator whine, it's caused by a failure of one or more of these silicon diodes. If you look at a normal alternator that's operating normally, and you put an oscilloscope across the output of the alternator or on the aircraft bus, you will see a very tiny amount of AC component, what we call ripple, that's typically only 1/10 of a volt, maybe 2/10 of a volt max, and it's small enough that it doesn't bother our avionics. On the other hand, if one of the diodes goes out in the alternator, then the output waveform gets real nasty, and in this case we've got a ripple that's about 8/10 of a volt peak to peak, and as you can see, it's a very nasty waveform that generates all sorts of horrible harmonics, and that's the kind of stuff that causes alternator whine in our radios. And if the If the bus voltage looks something like this, absolutely sure that the problem is a bad diode in the alternator rectifier. And since the rectifier is internal to the alternator, basically the alternator is going to have to come off and either be sent out for repair or exchange for another one. We talked about weak starter in our engine webinar last time, so I will just go through this very quickly as a matter of review for those of you who weren't here at the last alternator, the last webinar, but we spent quite a bit of time on this last time on the June 1st webinar, and all the details are up on the EAA webinar site. But again, if there's a problem with starting, the general procedure is first to see if it's a mechanical problem, whether the starter motor is turning, but it's not turning the engine because the mechanical interface between the starter and the crankshaft is slipping or not engaging. And as we talked about, TCM and Lycomings use a very different arrangement. Lycoming uses a gear engagement, which is either engaged or not, whereas TCM engines, I guess they're now CM engines. It's now Continental Motors because the Chinese bought them and Teledyne sold it. So I need to change these slides. But Continental engines use a clutch arrangement, which when it wears can start to slip. So the symptoms are you try to start the engine, the prop starts to turn, but when it gets to the compression stroke, it gets hung up and can't get past the compression stroke. Yet if you listen, you can hear the starter motor turning. It's just that the engine isn't turning, and that means that the clutch is slipping. If the problem is not a mechanical one, a slipping starter adapter, then it has to be an electrical one. And so we troubleshoot it much like we did the charging system failure. We check with the voltmeter to see if the starter is getting enough voltage, and we do this under load. We do this while we're trying to start the engine, put a voltmeter across the starter and see how much it's getting. Under the load of starting, the starter should get at least 2/3 of nominal battery voltage, so at least 8 volts on a 12-volt battery, at least 16 volts on a 24-volt battery. If the starter is getting enough voltage, but it can't turn the engine, then the starter's bad, so we're going to have to change the starter motor. If the starter is not getting enough voltage, then it's not the starter's fault, so we have to go and look further back. So the next thing we'll do is put the voltmeter on the battery and try to start the engine and see what the battery voltage is putting out under the load of starting. And again, it should be putting out at least 2/3 of nominal battery voltage, 8 or 16 volts. If the battery is not putting out enough voltage, then the battery's bad. We're going to replace it. If the battery is putting out enough voltage, but the starter isn't getting it, then the voltage is getting lost somewhere between the battery and the starter, and we have to check the components in between, which are typically the battery contactor, starter contactor, and various crimp connectors at the end of the big heavy starter wiring. Again, this is a picture of a TCM starter adapter to show that kind of weird clutch arrangement. The TCM starter adapter uses a part called a shaft gear, that thing on the left, which is geared to the crankshaft and has a knurled drum, and it has a big spring that has a very close tolerance fit on the outside of the drum. And when you start the engine, the spring grabs the drum and turns the crankshaft. And when the engine starts, the spring releases its grip on the drum, and the drum just freewheels inside the spring. And if the spring wears on the inside or the drum wears on the outside, eventually this thing will start slipping, and the starter adapter will have to be removed and repaired. Again, here's the schematic diagram. Just go over the same thing again in diagrammatic form. The first thing we want to do is make sure that the starter adapter is not slipping. In other words, that if the starter is turning but the engine isn't turning, then there's a mechanical slippage problem that we need to deal with. If it's not that, then we have to look for an electrical problem, and the first thing we do is to make sure the starter is getting enough voltage under the starting load. should be at least 2/3 of battery volt, nominal battery voltage. If it's getting enough voltage, then we have to replace the starter. If it's not, then we need to see if the battery is furnishing enough voltage under load. If it's not, we need to replace the battery. If it is, then it's getting lost somewhere in between, so we need to check under starting load what our voltage is after the battery relay and after the starter relay. There are some other places we can be losing voltage, like the engine grounding strap, because the starter normally is grounded to the engine and depends on the engine grounding strap to the airframe to provide a return path. So those are all things that we need to check if we've got a starter problem that's electrical. Final comment before we go to the questions. A lot of electrical problems happen only in the air and can't be reproduced on the ground. If you have a problem that only happens in the air and you can't make it happen on the ground, if you put the airplane in the shop, your mechanic will not be able to reproduce the problem, and so the only thing he can do is throw money and parts at the problem and use guesswork, which is not what you want. So problems that can only only happen while you're in the air, and a very large number of these electrical problems, ignition, noise, a lot of stuff we're talking about, only do happen while you're flying, then you're going to have to troubleshoot them in the air and figure out what's wrong before you put the airplane in the shop. Otherwise, as I said, you're just asking your mechanic to start using money and guesswork, which is not an optimum way to deal with problems. To troubleshoot problems in the air, we need to use our cockpit instrumentation. As I mentioned, every airplane should have a good digital voltmeter, and actually most do nowadays, because there's all kinds of equipment that we tend to have in our airplanes that do have the capability of giving us an accurate digital readout of bus voltage. If you don't have the necessary instrumentation in the airplane and you don't want to install it, you may have to just take a test meter along on a flight and hook it up to the bus, hook it up to the cigarette lighter socket or whatever is handy, so that you can monitor bus voltage accurately during the flight and see what's going on. More and more of us nowadays have digital engine monitors, which are fantastic because not only do they provide information to you in flight, but most of them capture that information, let you download it and analyze it on your computer or send it to somebody else to analyze. And digital engine monitors are among the most powerful troubleshooting tools that we have. I did a webinar a while back in this series, and I probably will repeat it, on digital engine monitors, but they're just one of the most powerful troubleshooting tools we have. And any airplane that does not have a digital engine monitor installed, I would heartily recommend that you consider installing one. They're absolutely worth their weight in gold, and they typically pay for themselves almost immediately in reduced maintenance costs. And finally, as we talked about, a lot of problems are troubleshot in the air in a very rudimentary fashion, simply by turning off switches, pulling circuit breakers, and seeing what you have to turn off to make whatever the problem is go away. And so we do a lot of fault isolation in that fashion. Anyhow, that's all I have in terms of prepared material tonight. As I said, it's a little bit shorter than usual, and so I would be happy to open things up for questions, Steve. And my email address is here on the screen, so anybody that has a question that doesn't get answered during the live session tonight, please feel free to email me, and I will attempt to get to answer all the questions that I receive. Steve?
All right. Wayne is wondering why you'd want to switch out the alternator out of line, for example, the split master switch.
Ooh, I don't understand the question. Every charging system has has some way of turning off the alternator. Usually it's a field switch. Sometimes it's a separate switch. Sometimes it's a switch that's combined with the battery master switch, either as a split switch, or in some of the real older airplanes, it's a single switch that turns them both on and off at the same time, which isn't a real great design, but some of the early airplanes did it that way. Occasionally there will not be a field switch; there'll just be a pullable breaker. But there needs to be some way to turn the alternator off and on. As I said, there are various ways of doing it, but normally in most airplanes there's an alternator switch, either a separate switch or a split master switch that has both a battery master and an alternator switch combined into a single unit. I don't know if that answers Wayne's question or not.
Well, if not, I'm sure we'll see a follow-up from him. And we're just, talking about, diagnosing problems in flight. It doesn't really hurt to turn an alternator off in flight, does it?
Absolutely not, no. And as I said, with an awful lot of the problems that we have to diagnose are typically isolated by turning various things off and on, and seeing what makes the problem go away. Not only doesn't it hurt to turn an alternator off in flight, but more importantly, and this is something that a lot of aircraft owners don't do but really ought to be done, it doesn't hurt to turn a magneto off in flight. In fact, on virtually every flight I do an in-flight mag check to check the condition of my ignition system. We've had an interesting rash of magneto-related failures. I don't want to spend too much time on this because the mags aren't really the subject of tonight's webinar, but just to illustrate this point, we've had quite a few emergencies declared because of magneto failure, and specifically because of magneto distributor gear failure, where some teeth strip off the plastic distributor gear in the magneto, and the magneto starts firing at random times and causing the engine to go berserk. I've followed a bunch of these incidents. Some of them have occurred at pattern altitude, some have occurred up at the flight levels, some have occurred with extremely high time CFIs at the controls, and in not one instance did the pilot have the presence of mind to try to turn off the bad magneto. Had he turned off the bad magneto, the engine would run perfectly fine on the good magneto, and it wouldn't be an emergency. He could proceed to wherever it was he wanted to go. But in not one case that I have followed did the pilot have the presence of mind to try turning off the magneto. And they basically declared an emergency and made a, kind of I guess I shouldn't say a forced landing, because all the ones I followed actually made it to an airport, but often not the airport they had in mind. I think this is a training issue, because it doesn't really, we have two magnetos for a reason, but the redundancy involved in having two magnetos doesn't help much if the pilot doesn't have the presence of mind to turn off a malfunctioning magneto and run on the one that's working okay. So that's a slight departure from what the question was, but I just wanted to mention it.
Okay, and we did actually get a follow-up from Wayne. He's, I guess it's a rather basic question. You can't turn an alternator off in a car, but why in an aircraft?
Well, you basically should be able to turn everything off in an aircraft, and if you have, smoke in the cockpit or something, it's very important to be able to disable whatever it is that's causing a problem. In a car, you can pull off to the side of the road and shut the car down. In an airplane, we don't have that option, so we really need to have the ability to turn off any electrical circuit that might be malfunctioning, either by turning off a switch or by pulling a breaker. And the fact that we can do that in an airplane is also very helpful when we need to troubleshoot a problem and isolate it.
All right. Jerry's wondering, he says here, are you saying I need to use shielded wire for the kill wire on my Aero V mags, which are Briggs & Stratton?
Well, let me preface this by saying that all of my experiences with certificated aircraft, I actually was up in Oshkosh 2 weeks ago, and Charlie showed me, took me through the Sonex factory, and I saw a bunch of AeroVs, so I at least know what you're talking about vaguely. But yes, what we call the P-lead, what you call the kill wire, really always needs to be shielded. Because otherwise it will radiate ignition noise and will frequently cause impulse noise to get into the radios.
All right. Bill's wondering, to check the voltage of a particular portion of an electrical system, do you hook up your multi-voltmeter in parallel to the circuit that you're testing?
Yes. To check voltage, different aircraft are different. Most metal aircraft use the airframe as a common ground, and so typically to measure voltage on a metal aircraft, you put the negative lead of the meter to airframe ground someplace, and you put the positive lead of the meter on whatever it is you want to measure, say the alternator field terminal. In composite aircraft and a few metal airplanes that don't use the airframe as ground, then you have to find a system ground somewhere. The only time that we put a meter in series with a circuit as opposed to in parallel is when we're measuring current as opposed to voltage. And occasionally we do that, but most of the time when we're troubleshooting, and in all of the instances that I illustrated tonight, we're measuring voltage, and so and the meter, yes, is in parallel with the circuit, but we don't actually have to break the circuit.
All right. Radio noise issue here. And Alan's asking if ignition noise would appear on both radios. Their primary radio, a GNS 480, occasionally gets a popping, boiling sound of interference. It doesn't matter who's talking, air traffic control or other aircraft. When it happens, they can switch to a number 2 radio, which is an MX11, which is clear, but not integrated into the 480 flight director. After a while, they can switch back to the 480, and it'll be clear. He was told that it was probably moisture in some connection. Now, the airplane's kept in a relatively dry hangar, and the last several flights they were in clear air. So does the moisture suggestion have merit, or do you think the ignition noise might be coming from some other source?
Well, I mean, first of all, you have to determine whether or not it is ignition noise. If it's ignition noise, then the moisture suggestion has no merit at all. And the way you verify that it's ignition noise is to, while you're in flight and you're hearing the noise, go to single mag operation, try the left mag, try the right mag, and if the noise goes away, then you verified that it's a mag and you have figured out which mag it is. By the way, common question that comes up, I will anticipate it. If you have a key type ignition switch that says left, right, or both, when you switch it to left, you are running on the left mag and the right mag is shut off. That's a question that frequently comes up, whether when you're on the left mag that means you kill the left mag or that you've killed the right mag, and the answer is if the switch is switched to left, the left mag is not grounded out, the right mag is. But in any case, the first step is to verify that it's ignition noise, and the way you do that is to shut off one mag at a time and verify that at least with one mag or the other, the noise goes away. That tells you for sure that it's ignition noise, tells you which mag it's associated with. And if it is indeed ignition noise, moisture is not going to be the issue. Now, that raises the question, well, why would he hear it in one radio and not the other? And the normal reason for that is that the two radios have separate comm antennas, and the comm antennas are mounted in different places. On my airplane, for example, the number 1 comm antenna is mounted on the bottom, on the belly of the airplane, and the number 2 comm antenna is mounted on the roof of the cockpit. So they're in different positions, and they would very likely pick up different amounts of ignition noise just because of where they're located. So that would be my best guess. Obviously, I don't know his particular aircraft, but I think that's the best answer I can give with the information I have.
All right. Does having the alternator switch in the on position during start cause a bigger load on the battery?
It does, but just a small one. The alternator the alternator draws maximum field current when it's stationary. In other words, when you've powered up the airplane, but before you've started the engine. A alternator in a 12-volt system normally will draw about 2 amps when the alternator is not turning at all, and once it starts turning, the field current drops quite precipitously, and the higher the RPM, the lower the field current. On a 24-volt system, it normally draws a maximum of about 1 amp. So it does put a load on the battery. It's not a very big load. Normally, I would recommend having the alternator on for start, among other things, for 2 reasons. One is to prevent the possible scenario that you will forget to turn it on and go flying with no alternator. And the other is that if you start the engine and bring the RPM up and then turn the alternator on, it puts a certain shock on the alternator to have the field turned on while it's rotating rapidly. It puts less stress on everything to have it turned on before you start. Although again, this is not a huge deal. The 2 times that I would consider starting the airplane with the alternator turned off, one is if you're starting on auxiliary power, on ground power, as opposed to on the ship's battery. And the second, and normally when you're doing that, the procedure is to turn off the alternator, turn on the battery, plug in the power cart, start the engine, have the power cart removed, and then turn the alternator on. The other is if you're starting on a very, very weak battery where you're concerned that it might not have enough power to get the engine started, by starting with the alternator off, you're reducing the load on the battery by 1 amp or 2. Those are the only circumstances under which I would normally recommend starting with the alternator turned off.
All right. Gary has some fluctuations in voltage readouts. He's got a JPI analyzer and a Davtron clock. In flight, the readings never match. JPI is always lower, sometimes to the point of momentarily giving an alarm, 12.2 volts. The ammeter always shows charge, and the battery minder shows a full charge. Does he have a problem, or any ideas that might be causing this?
Well, I don't know if I can ask a question of Gary and have him answer it, but I would be curious if the amount that the JPI is reads lower than the other voltmeters in the system is a constant value, or whether it varies all over the place. And if it's a constant value, I would be curious if that constant value is about 0.7 of a volt. And the reason I mention that is because it is possible, depending on how the JPI was hooked up, that there may be a diode between the bus and the JPI. And a silicon diode has a voltage drop across it of 0.7 of a volt. So if the JPI is low by 0.7 of a volt of the other things, it's probably because it's connected to a place in the aircraft that is diode isolated from the bus. If, on the other hand, the JPI jumps around a lot and the other voltmeters don't, then I would suspect that there may be either a loose power connection or loose ground connection or something that needs to be rectified.
All right. What's your opinion of using smart chargers while the airplane is on the ground? Using a smart charger is a good idea. It's a very good idea if the airplane is based in a hot climate, Phoenix or something, because the self-discharge rate of batteries rises extremely rapidly with temperature. It's less important for airplanes that are based in cooler climates. Also, I think it's more important to use a trickle charger if you are using a sealed battery like a Concorde or an Odyssey than it is if you're using a conventional flooded cell battery, because the sealed batteries
are less tolerant of getting discharged. We talked about this quite a bit in the seminar, in the webinar that I did on batteries. But generally, it's a good idea, and as I said, it's especially good idea if the aircraft is based in a real hot climate.
All right. What's your guideline in terms of resetting pop circuit breakers in flight?
Well, that's an interesting question. I mean, the general rule is you reset it. You wait a little while for it to cool off. You reset it once. If it pops a second time, you don't screw with it. We don't want to get into the Ricky Nelson syndrome. I don't know how many of you are old enough to remember the accident where Ricky Nelson died in a DC-3, but they had a combustion heater in that DC-3, kept popping its breaker, and they kept resetting the breaker over and over again, eventually to set the airplane on fire and killed everybody. So generally, the rule is if a breaker pops, give it a little while to cool off because they are thermal devices. Reset the breaker, and if it pops a second time, don't try to reset it again. Just land the airplane.
All right, and here's one that's, he says, it's a very basic question, but what is the bus system in the airplane? When the airplane is running and I read voltage on the display on the JPI, is he seeing what's on the bus, or is that the battery voltage?
Well, obviously it depends on how the JPI is hooked up, but normally the JPI is connected to either the main aircraft bus or the avionics bus, depending on how it's wired up. Some aircraft just have a single bus, and a bus is basically just a big conductor, often a piece of copper bus bar, but it can just be wires that connects one side of a whole bunch of circuit breakers together, and provides the basic power source that all of the individually protected circuits are connected to. Some aircraft have, or many aircraft have, a separate bus for avionics with an avionics master switch that can be turned on and off. Some aircraft have a hot battery bus, which is a bus that is hot continuously even when the battery master is turned off, and is used for things like clocks and courtesy lights and things that you want to operate even when the master switch is turned off. Some aircraft have what's called an essentials bus. That's typically aircraft that have dual electrical systems, a primary system and a backup system, let's say like a Cirrus, where if the main charging system fails, there's a backup alternator and a backup battery that supply power to what's called an essentials bus, to which is connected just enough stuff to keep you flying. So it varies a lot depending on the aircraft design, but basically a bus is just a big heavy conductor that connects a whole bunch of circuit breakers together on one side, and is typically connected to the battery and the alternator when we're flying.
All right, George has a 1980 F-33A, and normally he sees a JPI bus voltage 28.3 volts, but intermittently it has been getting a 25.4 reading. He's changed the battery, it still occurs. Any ideas where to start looking for the problem?
Well, that's not going to be a battery problem for sure. If the voltage drops to 25.4, it basically means that the alternator has stopped supplying power, and the aircraft's running on battery power. So whatever is wrong with his airplane is not a battery problem, it's a charging system problem. I'd need more information to be able to troubleshoot it. For example, when it drops down to 25 volts, does it come back all by itself, or does he have to cycle the alternator switch off and back on to bring it back? Frequently, it will be an overvoltage trip out that takes the alternator offline. And but again, I don't know his exact symptoms. One of the things that he can do if he wishes is to dump his JPI data and email it to me with a little description, so I remember who it is and what the problem is, and I'll take a look at it and see if I can figure out anything just from looking at the JPI readout.
All right. Talking about the ground for the alternator, if the ground fails for the alternator, is there still output?
No, of course. If the ground fails for the alternator, it can't put out any current because the circuit's broken. Again, normally, most of the time, and there are a lot of different variations in the electrical system, but most of the time the alternator, the negative terminal of the alternator is grounded to the engine case. And then if it's a metal airplane, the engine case is typically grounded to the airframe with a big braided strap. If it's a composite aircraft, then the engine is grounded to the electrical box that has all of the big heavy-duty stuff in it that is sometimes called a J box or an MCU or whatever it is, because the airframe not being metal, cannot be used as a ground, so it has to be grounded somewhere else. But typically an alternator is grounded to the engine case, and then the engine case is grounded to whatever the ground point is on the electrical system. That's not true of every aircraft. There are a lot of different variations, but that's the most common arrangement.
All right. Robert's engine monitor also monitors the exhaust gas temperatures. Signals are typically 20 to 40 millivolts. Now, when his strobes are turned on, the temperatures go crazy. Would it help to install a large capacitor in the power lead to the engine monitor? Would that help that problem?
Probably not. It sounds to me like his engine monitor is probably not grounded properly. I've never seen a case where an engine monitor that was grounded properly had strobe noise in the signals. So the first thing I would do is see where the engine monitor is grounded. If the engine monitor doesn't have a really short path to a good solid airframe ground, and has some long wire going somewhere to ground it, then that wire can serve as an antenna. As he points out, the signals from thermocouple probes that most engine monitors use are in the millivolt range, and so these things are extremely sensitive to grounding problems, and we see those all the time. So I would not put a filter in the power supply to the engine monitor. I would check the grounding and make sure that it's short and very low impedance.
All right. Kind of a follow-up question. You just mentioned recording the JPI's voltage. Do all of the JPI systems record? He's not seen it on his EDM 700.
I'm pretty sure that all the EDM 700s record voltage. I'm pretty sure the answer to that is yes.
Time to read the manual.
It may not show up on the cockpit display by default. It may be something that you need to program to see. But I'm pretty sure that whether you see it on the display or not, it winds up being captured in memory.
Okay. If Stu is checking the voltage directly at the battery and compares that to the readings of digital voltage on the engine monitor is always reading 0.1 to 0.2 volts lower than the reading at the battery. Is it normal to have that much of a difference?
Well, if it's only a tenth or two less, then that's quite possible. I'm not sure what kind of aircraft this is where the battery is mounted, but a couple of tenths of a volt drop between the battery and the bus is not out of line, particularly if the path from the battery to the bus is fairly long. I'm thinking, for example, of say a Cessna 182, where the battery is mounted way back in the tail, and the wire that goes from the battery to the bus is, I don't know, 8 feet long or something like that. It will vary from installation to installation, but if the difference is only a tenth or two, then I wouldn't be too concerned.
All right. We have a Citabria 7 KCAB. They've replaced the battery several times. The starter's been replaced once, and without resolution of the problem, which is it's got weak starting, and also evidence of the battery going dead over time, about a week, unless they put a charger on it. The master's off, and any ideas on where to start looking for where the power drain might be?
Yipes. Well, if the battery is going dead in a week with the master switch turned off, there's something terribly wrong here. And I mean, the very first thing I would do is remove the positive lead from the battery and insert a test meter in there and measure the how much draw there is. And it should be either 0 amps, or it should be something in the very small milliamp range if there are hot wired things like clocks or something in the airplane. But it sure shouldn't be more than 10 or 15 milliamps that's being drawn from the battery when the battery master switch is off. And if it is, something is wrong and needs to be run down. By regulation, and of course the Citabria is a certificated aircraft. By regulation, anything that is hot wired to the battery, in other words, that it continues to be powered up when the master switch is turned off, is required by regulation to be protected by a fuse. And that fuse normally has to be within a couple of inches of the battery itself. So normally, if the aircraft has hot wired items, as I said, like a clock or a courtesy light or something that is energized even with the master switch off, or a Hobbs meter, for example, is another example. It would be protected by a fuse, and the fuse would be essentially co-located with the battery, wherever the battery happens to be located in the Citabria, whether it's on the firewall or wherever. And very frequently you will see a set of fuse holders mounted right next to the battery, and those are typically for those things that are hot wired to the battery. So if there's any kind of significant draw from the battery with the master switch turned off, typically you can isolate that simply by pulling one fuse at a time and seeing when the current draw goes away which fuse it is you pulled, and whatever that is going to be the culprit. But boy, if the battery is discharging in a week, that's pretty serious. Something pretty significant is wrong.
All right, and just a quick follow-up to that. Thank you for your suggestions, but they were suspicious of possibly the battery solenoid causing that discharge. Any thoughts along those lines?
Well, I'm not sure what they were suspicious of. If there are only two things that can fail with a battery solenoid. One is that the contacts are welded, and when you turn the master switch off, it doesn't disconnect the battery. And I assume that's not the case, because otherwise you'd know it. I mean, when you turn off the battery switch, presumably your radios and your terminal bank and all that other stuff goes off. So it probably can't be that. And the only other thing that could be wrong is that when you turn off the battery switch, somehow voltage is still being applied to the battery contactor coil, and that would either be a defective master switch, which would be pretty unusual, or sometimes there's a diode or something across the battery switch for arc suppression, and I suppose it's possible that the diode might be shorted. But it sure doesn't sound to me like a battery contactor is a very likely explanation for this.
All right, and our last question for this evening, is probably the most creative. Dennis wants to know what causes ground loops. Now, in flying terms, that's not flying your tail dragger all the way to a stop at the chocks, but I'm getting the feeling what he's maybe getting after here is is what's commonly referred to as a ground hum, or in electrical in household it's the 60 hertz hum. But what causes those things to occur?
Well, a ground loop is simply a situation where different components in the airplane are grounded to different places, and there's a non-negligible resistance between the various grounding points, so that a non-negligible voltage drop can occur between different things that theoretically are all supposed to be tied to ground. In a perfect installation, everything in the airplane would be grounded to a common point. And in fact, in a lot of the new designs, and in particular composite airplanes like the Cirrus, where the airframe is not used as part of the electrical circuit, that's exactly how the electrical systems are designed. There's just a kind of a common ground bus right at the master junction box. It's sometimes called a J box if it's in a new Cessna, or an MCU if it's in a master control unit if it's in a Cirrus, and everything is grounded to a common point. In older airplanes, and particularly in spam cans like I fly, where the airplane's made out of metal, the common practice was always to ground each component to some convenient hunk of airframe that's nearby, and that works okay as long as there's essentially zero resistance between all the different grounding points. But over time, as things start to corrode in these aircraft, we start to actually get non-negligible resistance in the grounds, and we start to get voltage drops that cause mischief, like the hum that you were talking about. Again, the best way to wire up an airplane, if you're doing it from scratch for the home builders in the group, is to have one common grounding point and ground everything to it, which is typically the way modern composite airplanes are designed, but is not the way that older metal airplanes were traditionally done.
All right, Mike, we've pretty much taken up our time, and appreciate everyone joining us this evening. Any final words of wisdom for us?
No, I think I'm depleted of wisdom, to be honest with you. Just want to remind everybody that the next webinar in this series is going to be on August 10th, which is the second Wednesday in August instead of the first, and the subject will be kind of an interesting one: owner-produced parts for certificated aircraft, and we'll be getting into the arcane and very interesting FAA regulations that allow owners to fabricate parts for their own certificated aircraft. It's kind of an interesting subject. We've had a lot of questions about it, and so I decided we'll do a webinar on that subject, and it will be on Wednesday, August 10th.
All right. Thank you, Mike. Thanks for joining us. And again, as you can see on the schedule, August 10th, mark that on your calendar for Mike's next webinar that you'll hear right here on EIA.org. If you are interested, you're thinking about flying into AirVenture, tomorrow night you should tune in for Fred Stadler's presentation on a first-time flyer's guide for flying into AirVenture. He is very up on the NOTAM and the procedures, and will be able to walk you through it. If you've never done it before, this is a must-attend webinar, and even if you have flown in before, I'm sure Fred will have some great tips for you. So with that, we're going to close out tonight's broadcast. Again, thank you for being a part of our webinar this evening. As I mentioned earlier, there will be a short survey that pops up when you log off. If you would just take a moment and fill that out, we'd really appreciate that. Otherwise, have a great evening, and we'll talk to you at our next webinar.